Hello. In most archaeology, we're dealing all the time with samples. It's pretty rare to excavate an entire site or to have a collection that consists of all of the artifacts or seeds or bones or whatever that come from that site. So we have to deal with samples. It's very important for certain kinds of research projects to ensure that that sample is representative of the bigger population that we're interested in. So today's video is going to cover sampling methods to give you some idea of what strategies you can use to ensure the validity of results that are based on samples. Now, sometimes we want to sample a collection that already exists in our lab or in a museum or something like that. So in this case, the population does not consist of all the artifacts that come from a site or whatever. It consists of the population of artifacts sitting in a collection. When we do that, we have an advantage in that we can simply number all of the artifacts and then take a random sample from them, or a systematic sample or something like that. But here I'm going to demonstrate how you would take a random sample of a collection when you already know what all the artifacts are. Now, ordinarily, you would only do that if you have a very large number of artifacts. So, for example, if you had thousands of tools like this one in a collection, and you figured you only had time to analyze a few hundred of them, it might make good sense to randomly sample the ones that are available to you. In this case, I don't have thousands. I only have, I think it's 26 in the tray here, but just for demonstration purposes, that will do. Ordinarily, you would have a lot more than that. So all we have to do then is arbitrarily number these things, in this case from 1 to 26. I think there's 6 there, 6 there, 6 there, and a few more here. So we've just arbitrarily number them in order, and then we pick random numbers in order to decide which of those ones are going to be in our sample. Now, one way you can get random numbers is to go to a statistics textbook, where you'll find in the back, usually an appendix that has a random number table. And you just make up a rule about how you're going to essentially sample the random number table. So you might decide, kind of blindfold yourself and kind of arbitrarily stick your finger on the page, or one of the pages, to find your starting number, which in my case happens to be 50. And then, assuming I want a 2-digit number, because you can interpret these as being 3-digit numbers, 4-digit numbers, whatever. But in this case, I'm going to use a 2-digit number because I only have 26 artifacts. And the first number I end up with is 50. I don't have an artifact 50 here, so I skip that. And then you have to have a rule as to where you go next. It could be you just go across the rows or down the columns, or you could go every third one across a row or a column, or you could go diagonally on the page. So let's just say I decide to go every fourth one down the column until I run out of space. So that would be 1, 2, 3, 4. Next one is 14. So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14. That means this one gets selected for analysis. And go down another 4, I get 54. It doesn't appear here. 1, 2, 3, 4, 53 I don't have. 3, 4, 24. I do have 24, I think. 6, 18, 19, 20, 1, 2, 3, 24. Anyway, you can see that can work. It's not the most efficient thing to use, especially if you're going to end up a lot of random numbers that don't apply to your collection because they're too high. So it's not the best way to go. But you could use that method if you wanted to. So if you're desperate to find random numbers, this is a good way to do it, but you'll have to skip a lot of them because some of them won't apply. A better way these days is to take advantage of your computer to get random numbers. Now, some of the software you probably already use will generate something that's called random numbers. Various spreadsheet programs and whatnot usually have a random number function in them, and you can use those. They actually generate what are called pseudo-random numbers. They're actually not truly random because they're based on an arithmetical algorithm, but they're probably close enough to random numbers to be pretty useful. However, if you want to make use of genuine random numbers, there are also websites you can go to that will generate those for you. So that's what I've done. I went to a website that generates actual random numbers. And one of the advantages of using those is that unlike the random number table where you're kind of stuck with what you got, you can dictate what range of numbers you want to select from. So in this case, we have 26 artifacts, so I can say I want 10 or 12 or however many random numbers between 1 and 26, or from 1 to 26 inclusive, which is what I've done here. Now, this particular random number generator actually generates them true random numbers so that you could get some numbers duplicated. So if you want to sample without replacement, then you would have to ask for a few more random numbers than you actually need, because you're bound to get at least some numbers repeating. So in this case, if I want 10 artifacts, I want to ask for at least 12 random numbers. In fact, here, to be on the safe side, I've asked for, I think it's 15 or 16 or something like that. So putting these back for a second, I think this one is down here. My first random number, this is going to be a lot more efficient because there will be no wasted numbers except for the cases where they're repeated. My first one is 11, which I believe is this one here. Then I have 21, so that was 6, 18, 19, 20, 21, and 7, that will be this one. 19, that will be this one, I think. 6, 6, 12, 13, 14, 15, 16, 17, 18, no, 19 is that one. 14, 8, I need 2 more. 3, that one, and 10. 6, 7, 8, 9, 10. Okay, so I now have 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, 10 artifacts in my sample. And in this case, I was actually kind of lucky I didn't get any repeated numbers. But usually if you have a larger sample size than 10, you're going to get at least some repeated numbers. So that's one way to select a random sample, but the trouble is it only works in cases like museum collections or laboratory collections where the population is already known and you can actually make a list of every item in the population. But in typical archaeological situations, that's not what we have. For example, our samples come from sites that have not been excavated yet, perhaps, or sites that have been excavated, but the excavation only provides a sample of that site. So you have to, whether or not you have control over how the site was sampled, or the region was sampled if we're talking about a survey, you have to take into account how the sampling was done in the field at the same time that you're doing your sampling for your laboratory work, because you're most of the time already dealing with samples. So you don't have a population, except in the case where we want to assume that the collection is the population, which is not an ideal kind of population because we have to then assess whether or not there was any bias involved in the selection of items in that collection. So today I'm going to tell you a little bit about some of the strategies we can use for sampling that inevitably include kind of a field component because we have to take that field work into account when we do our sampling. But then, what we can do in the lab, because most of the time, even when all the artifacts from an excavation or survey are available, quite often we have to still subsample that sample in order to kind of cut down the amount of work that's involved in doing an analysis, especially when the number of objects that were excavated or surveyed is extremely large. Sometimes archaeological populations have structure in them. For example, a site can be structured spatially or stratigraphically or both. When we have structure, there's always a risk that a simple random sample would omit some significant parts of the population. In the case of this pueblo, for example, it's conceivable that a random sample would omit the kiva entirely. A solution to this is to stratify our population. What that means is subdividing the population into subpopulations that are internally homogeneous but differ from stratum to stratum. In this example, we might have reason to believe that the kiva might differ from the courtyard, and both of those might differ from each of the 3 room blocks marked in different colors here. So instead of randomly sampling the whole population at once, we randomly sample within each of these 5 areas. In many cases, we're not fortunate enough to have any indication of structure in a site before we sample it. It all looks pretty much the same, and we have no basis for stratification. In others, though, we sometimes get some clues in the form of perhaps hollows in the topography that might indicate pit houses, or even visible wall lines where there is mud brick or stone architecture. And we can use these as a basis for making more informed decisions about a stratified sample for the site. What doesn't tend to work very well is just to arbitrarily stratify the site, because you really need to have some kind of basis for information about variability across the site. But that could even be as little as differences in the density of certain kinds of artifacts on the surface of the site. That could be a basis for stratification. When we are lucky enough to have visible wall lines, as in the case of some pueblo sites in the American Southwest, for example, we have a much more solid basis for making stratified samples. When we take the same sampling fraction from each of the strata, say 20% or 30%, the result is a proportionate stratified sample. If the sampling fractions differ among strata, then we have a disproportionate stratified sample. Disproportionate stratified samples require weighting factors in order to avoid biases in the resulting statistics. This usually results in a more representative sample of the population when the population has structure. So we might decide to randomly sample perhaps 20% from each of these things, although if they vary a lot in terms of their individual sizes, like how many artifacts are in each of these clusters, taking a sampling fraction that's consistent among all of them might not be such a good idea. So we might want to use either a disproportionate stratified sample, treating these as our strata, or we might want to decide what is the minimum sample size we need from each of these units. And there are a number of methods you can use to estimate the sample size you need in order to get reasonable results. So these two clusters, for example, actually these three clusters only have 3 artifacts in them. So for one thing, we couldn't take a 20% sampling fraction anyway because it's not easily divisible by 5. But in addition, that would probably be a fairly crummy result. So we'd probably, since these ones only have 3 in them, we'd probably want to take at least 2 from each of those, and maybe all 3, because even that only gives us a sample size of 3. Whereas these other ones that have a lot more artifacts, we could, instead of taking, again, 20%, we might decide it might be okay to take 5 from each of those, and that might give us reasonable results. Of course, in reality, the clusters you would likely have a great many more artifacts than this, so we would be selecting sample sizes of, say, at least 30 or 50 or 60 or even 100 from each of the clusters in order to make sure we have a fairly reasonable sample. So we could use, if we're going to randomly select within these clusters, we could use a random number table or a website that generates random numbers in order to help us select them. So we might arbitrarily number the artifacts within each cluster from 1 to 100 or whatever it might be, and then randomly pick numbers within that range to decide which ones get removed to become members of our sample. So we might decide we're taking 5 from here, and they're selected randomly, and we take another 5 from here, and we take perhaps all 3 in each of these clusters. And that constitutes the sample we're going to use. But because they're unequal sampling fractions, we have to remember this would be a disproportionate stratified sample. So we have to take that into account when we measure descriptive statistics or do any statistical tests on these artifacts. Unfortunately, in archaeology, it's usually not possible to take random element samples of artifacts, because we find the artifacts buried in the ground rather than on the shelves of a museum. So the population, in fact, is unknown to us until we start excavating. So by and large, archaeologists tend to make use of cluster samples. What this means is that rather than randomly or systematically sampling all the artifacts that are in a site, or all the sites that are in a region or something like that, we tend to do things like excavating certain locations within a site, and then we have all the artifacts that come from those excavations, at least as long as we were very thorough in our recovery. For example, when faced with an archaeological site like this one, outlined by the dashed lines, we might decide to take a random spatial sample of square areas on the site. We use pairs of random numbers as coordinates to establish the locations of the squares that will be included in our sample. Here we end up with a sample size of 8, or 8 clusters. In cluster sampling, we effectively have 2 kinds of sample sizes. One, represented by M, is the number of artifacts or bones or seeds or whatever, while N is the number of clusters, in this case 8. In those 8 clusters, we might have more than 1,000 of the items that we're interested in. So for example, these trays I have on the table here might represent the artifacts that were found in 5 different excavation units on a site. They might be of standard size, these excavation units, or maybe not. They could also have been randomly selected within the site, in which case we would have a spatial random sample of the clusters. But then typically what we have at the end of the excavation is sets of artifacts that come from each of these excavation units, each one of which is a cluster in a cluster sample. Now, what that means is that we still have a pretty good representation of the artifacts in the site, as long as these 5 clusters are a pretty good approximation of what we would find if we took another 5 clusters somewhere else. So one possible approach here is to take all of the artifacts from all 5 of these excavation units and treat that as our sample, in which case we have a cluster sample of the artifacts in the site. Another thing that can happen, especially when we have either a large number of excavation units, too many for us to analyze in their entirety, or the number of artifacts in each of these clusters is extremely high, much higher than what we see here, we might actually then subsample. Instead of analyzing all the artifacts from all of the clusters that we excavated, we might actually only analyze a subset of them. If that happens, we have a number of options. One is to treat the excavated assemblage as though it's a population, and we just want to understand what are the characteristics of that collection. Or we can treat all the artifacts in the site or in a particular layer of the site, or a stratigraphic unit in the site or whatever, as the population, in which case we have a cluster sample from that, and then we're doing a multi-stage sampling by sampling within the clusters. Now, one approach would be to say, okay, we're just going to analyze from one of the excavation units. This one seems to have the most artifacts, for example, so we'll just take that one and we'll analyze those. That approach would presume that we think that this collection is a reasonably representative sample of the whole population in the site. And maybe partly because it's a relatively large sample, it might not be too bad. One of the reasons why that tends not to be a very good approach in archaeology, though, is because of something called spatial autocorrelation. That means that things that are found close together in space tend to be more similar to each other than ones that are found far apart in space. So to put it another way, if we have a reasonably large archaeological site, it's conceivable that most of the flint knapping was done in one part of the site. Most of the houses are in another part of the site. Most of the pottery making was in some other part of the site. Most of the butchering only took place in 2 or 3 parts of the site. So that if we only excavated one part of the site, it's fairly unlikely, at least in the case of a large complex site, that we're going to capture all of the variability that's in that site. So excavating and or analyzing material only from one restricted spatial area within the site is, generally speaking, not a great idea. So we'd probably be better off if we didn't have time to analyze all the artifacts from all 5 excavation units, at least to subsample those 5 excavation units and treat it as a kind of stratified sample instead of just taking one of them and treating that as though it was representative of the whole site. So as long as these 5 clusters are fairly well spread out on the site, we at least have a better chance of representing the site's variability. Sometimes in that situation, we use multi-stage cluster samples. For practical reasons, rather than taking a random sample from every cluster, it might make more sense to randomly select a few of the clusters for analysis. For example, we might have 15 different excavation units scattered across a site, or 15 different features within an excavation from which we want to select 5 randomly. The entire contents of these 5 excavation units or features then become our sample. If instead of a whole site, our population consisted of a pueblo like this one we used before, we might decide to use a stratified cluster sample. This time, let's stratify it a bit differently on the assumption that the back rooms are probably different from the front rooms in the pueblo. Our population will consist of all the rooms in the pueblo, plus perhaps quadrants of the courtyard and kiva areas. We could randomly select 2 rooms from each of the room block strata, and perhaps 2 quadrants from both the courtyard stratum and the kiva stratum. Then all the artifacts found in each of these selected spaces, as represented by the bags here, constitute our sample. Most of the descriptive statistics for cluster samples are pretty straightforward. To calculate a mean, for example, all we have to do is sum together the values for all of the items in our sample and divide by the total number of items. Similarly, for a proportion, all we have to do is count how many of the m items have a particular characteristic and then divide that by the total value of m, in this case 1000. However, calculating a standard error is a little bit more complicated because we have to take into account the number of clusters and not only the number of items. For each of the n clusters, we have to calculate a separate local estimate of the descriptive statistic. Then we subtract each of these from the global estimate calculated from all m items. These are called the deviations from the mean or proportion. For example, in this fictitious data set used to calculate mean rim diameter for some pottery, the deviations range from -3 to +4.5. We square these and then sum them to obtain the value of 35.3. To obtain the standard error, the first thing we do is take that 35.3 and divide it by n-1, which in this case is 4. That yields 8.8. We then divide that by the sample size in terms of clusters, which is 5, which yields 1.8, and take the square root to obtain a standard error of 1.3. So we can now report the mean diameter as 14 plus or minus 1.3 centimeters. However, if the total number of clusters in the population is pretty small, you might want to use the finite population corrector. In the example we used here, the number of clusters in the entire population was only 84. The finite population corrector is 1 minus the sampling fraction, which in this case yields 94%. We then follow the same procedure as before, except that we multiply by 0.94 before we take the square root. In this case, it makes virtually no difference because our sampling fraction was so small. In archaeology, there are certain kinds of analysis that are so costly in terms of the number of hours involved in analysis that it's absolutely necessary to do some kind of sampling, and generally speaking, it's cluster sampling of sediments by very small volumes of sediment, or at least relatively small volumes of sediment. So for example, an archaeobotanist wanting to understand what kinds of seeds and how many seeds of various types are present in archaeological features might take 10 liters of sediment and do flotation on that sediment to reduce it down to a smaller volume, and then perhaps subsample that again in order to analyze whatever seeds and charcoal and so on are in that sediment without examining the entirety of the 10 liters, let alone the entirety of the feature. So in a case like that, what we have is a cluster subsample or a multi-stage cluster sample. Among the things we need to consider when we're doing cluster sampling for very small things like seeds and fish vertebrae and so on in sediments is not only the sample size in terms of the numbers of seeds or the numbers of fish vertebrae or whatever the case may be, but also the sample size in the terms of the number of sampling elements, the number of clusters, if you will. How big should those be in order to get reliable results? Turns out there's quite a trade-off here because we could have a very large number of very small volumes. This little vial here holds 10 milliliters, for example. This one holds only 3 milliliters. So we could use, if we use very small clusters like this, we can get a very large N, a large sample size in terms of the number of clusters. Or with the same amount of effort, we could get a smaller number of somewhat bigger clusters using a 33 milliliter vial like this old film canister, or a very small number of clusters, and so very low N, but a very large volume for each cluster. So, if we used a large beaker like this. So we have to figure out what's the best balance between the size of the sample elements, the number of sample elements, and the number of seeds or fish vertebrae or whatever we're going to find in those sediments. So remember, in terms of cluster sampling, N is the number of clusters or sampling elements, which in this case are volumes of sediment, perhaps being 3 milliliters or 10 milliliters in size, or 10 liters in size. And on the other hand, we have M, the sample size in terms of the number of seeds or fish vertebrae or whatever else it is we're looking for. For example, We might have a cluster sample with 4 beakers filled with a mixture of sand and charred seeds. In that case, our sample size n is 4. When we empty the sand onto a petri dish and remove it so that we can count the seeds, we might find 186 seeds, or m equals 186. If we make some assumptions about the likely density of the small items that we're interested in analyzing in the sediments, we can actually use a mathematical approach to try to determine the optimal balance between the size of the sample element, the number of sample elements, and the density of the seeds or vertebrae, and our expectations in terms of confidence limits and that sort of thing. But for most of us, a simpler solution is to take a pilot sample, particularly since we don't know in advance what the density of the seeds or vertebrae or whatever is. Take a pilot sample and we experiment with different sizes of sample elements to find out what the results are like. Because one of the things that happens, of course, is, like for example, in this case we have a bin filled with sand and some seeds, just for the purposes of this experiment. And if we take a very small sample element, the 3 milliliter one, it's fairly highly likely that when we empty this on a petri dish for examination under the microscope, that a great many of those sample volumes, including this one, have no seeds in them at all, because the density of seeds in the sand is such that the expected number of seeds per 3 milliliters is less than 1. So we're likely to get a lot of zero values when that happens. If, on the other hand, we use the 10 milliliter vial, and we just kind of arbitrarily grab some sand there and we make sure it's leveled off to 10 milliliters, and empty that in the petri dish, we get several seeds in it, because there is more than 3 times the probability of having seeds in the petri dish than in the 3 milliliter one. And of course, if we use a much larger sample element, like this 33 milliliter one, it's virtually certain that we're going to get a certain number of seeds in there, and in fact we're going to get several in them. Now clearly, in terms from the perspective of individual clusters, the bigger the sample element we use, the more likely it's going to be representative of the population that we're trying to sample. But at the same time, we have to sacrifice sample size in terms of n, because if we tried to count all the seeds in a volume of sand this big, it would take us a very long time. So we might have only a sample size of 1 or 2, when we really want to have sample sizes considerably larger than that. When we take a cluster sample from a sediment volume in which the items of interest are pretty low in density, there's always a risk that some of our clusters will have none of those items at all. If we're really unlucky, as in this case, we could end up with a very poor estimate of the density or number of items in the volume of sediment. For example, let's say the density was 200 items per liter of sediment. In that case, the average number of items in each of our vials would be about 2. This is called the expected value. And when the expected value is as low as that, the laws of probability tell us that we can expect no items at all in about 14% of our vials. We can do similar probability calculations for other sizes of sampling element. For our example, you can see that a 3 milliliter sampling element would perform really poorly, while one bigger than about 30 milliliters would perform quite well. To give a visual sense of those numbers, let's do a sampling experiment with a 1/3 sampling fraction of a half liter of sediment. For sampling elements of 10 milliliters, that would mean a sample size of 17. In this case, we had a rather lucky result with only one vial that was completely empty of the items of interest. Most of the time we'd expect about 14% of the vials to be empty. If we switch to sampling elements of 3 milliliters, our equivalent sample size would be 55. You can already see that with a density of 200 per liter, we can expect many empty vials. In fact, in this case, at the end of the experiment, more than half of the vials have no items in them at all. This would likely lead to poor statistics. When we turn to sampling elements of 33 milliliters, the equivalent sample size is 5. Although they vary in density, none of the beakers is devoid of the items of interest, and this sample would likely lead to accurate and precise estimates of the number and density of the items. Furthermore, with n equals 5, we would end up with a much smaller standard error for those densities or numbers than we would had we taken a single large beaker with 165 milliliters of sediment, and n of only 1. Of course, those were just simulations, and in real situations, we wouldn't know what the density of items was. So we usually either have to make guesstimates, or else use a small pilot sample to get a rough idea of the density that we can expect in the sediment we're going to sample. I hope that helped you understand the different kinds of sample that there are, the different sampling strategies, and how you can decide which sampling strategy is best for your particular research project. I also hope it helped you understand what to do with the data that result from those samples. If you would like to learn more about this topic, you could consult Chapter 6 of my book, The Archaeologist Laboratory, available from Springer. Thank you, and stay safe.